Hello, welcome to lecture 23 of Electrical Circuits 1. Today we're going to talk about the step response of second order circuits. So today I'm going to present the governing equation, the solution in mathematical form, but I don't want to dwell a lot upon the mathematical expression for the step response. What I want to do mostly is estimate the step response directly from the differential equation coefficients. I want to do as little work as possible in order to get an idea of what the solution looks like. Okay, every time I'm confronted with a second order system, I don't necessarily want to solve a second order differential equation. I want to get an approximate solution that's reasonable. I can get that from the coefficients of the differential equation without directly solving it. Finally, we'll do several examples of second order system step responses. The associated educational material is in sections 2.5.5. Our governing equation is going to look a lot like the natural response equation. It's still in this standard form, d squared y dt squared plus 2 squiggle omega n dy dt plus omega n squared y. However, rather than having this expression be equal to 0, it is now equal to our forcing function, which is a unit step multiplied by some scaling factor a. So my input is 0 for times less than 0 and a for times greater than 0. Now, in order to simplify our analysis, when I'm talking about the step response of second order systems, I'm going to assume that my initial conditions are all 0. So the value of the function itself at time t equals 0 is 0, and the slope of the function at time t equals 0 is also 0. These conditions correspond to a condition in which the system is initially relaxed. As we said, when we mention that the system is relaxed, it means that we have no energy stored in any of the energy storage elements in the system. That will correspond to this condition. Under these circumstances, the mathematical solution for the step response of the second order system looks like this. I don't want to get too much into the details of this other than just to mention that we have sinusoids, cosine omega dt and sine omega sub dt, where omega sub d is our damped natural frequency. So we have sinusoidal terms here and a decaying exponential multiplying those. Now, as in the case of the first order system, our step response is the superposition of the input function, which is constant, and the natural response, which is this term here. So this 1 comes from the forcing function. We have a scaling factor on the whole thing, which is proportional to the input value that we apply to this. So what we get is it looks like a natural response superimposed with a step function. Now, what I'm going to start doing now is looking at several parameters specific to the step response. And as I mentioned earlier, our goal is going to be to get a quantitative estimate of the system response without actually solving the governing differential equation. So I won't get a mathematical expression for y of t, but I'll try to estimate the pertinent points, the pertinent parameters that I need to know about the output. So what happens is that several of the parameters that we'll see in the response are directly related to the coefficients of the governing differential equation. Once we've made that mapping, all we need is the differential equation itself to estimate the response. So what we'll do, ultimately, okay, the flip side of this problem is to take a measured step response, okay, so we can take some unknown second order system, we can apply a step input to it, we can measure the output in the lab. From that, we can estimate the differential equation governing the system. This is an extremely important type of problem. Sometimes when you're modeling a system, you don't necessarily know all of the physical parameters that are in the system. Some of the resistances may be unknown. Maybe you don't exactly know the values of the capacitance. So you run a test to see if you can estimate your differential equation. This process has a name. It is called model parameter estimation. You use data to estimate these model parameters. So up here, we'll take a look at the differential equation coefficients, try to estimate the response. Down here, we take a measured response, we try to estimate our differential equation coefficients. Okay, the step response of an underdamped second-order system, and I want to emphasize that my discussion from here on out will be strictly related to underdamped systems. Okay? We will have oscillations in our response. So the step response of an underdamped second-order system will typically look something like this. There are a number of parameters that are commonly used to quantify this response. One of them is the steady state response, which I've called Y sub SS. It's the final value that this step response goes to. Another thing that people tend to be particularly interested in is the maximum value achieved by the step response. I've denoted that as Y sub P for the peak response. The final thing that people commonly use to characterize a step response is the rate at which this response is coming up. That's typically quantified by what is called the rise time, which I've denoted as T sub R. The rise time is the amount of time required to get from 10% of the steady state response to 90% of the steady state response. This is kind of a measure of the frequency of the oscillations in this response. More importantly, what it's used commonly to characterize is the speed at which the system responds. A short rise time corresponds to a system that's responding faster than one with a long rise time. So now we can take these parameters and use our differential equation coefficients to estimate what these will be. That will give us an ability to at least sketch an approximate step response. The first step response parameter I want to talk about is the steady state response. If we look at our original governing differential equation, it hasn't changed since a couple of slides ago. Our forcing function is a scaled step. This is just a number for time greater than 0. So if I let time go to infinity, the only thing that's left of this is the particular solution. The particular solution has the same form as the forcing function. Therefore, y of t has to become a constant. Okay? Another way to look at this is the right-hand side of this equation is a constant as t goes to infinity. Therefore, the left-hand side of this equation must be a constant as t goes to infinity. If the left-hand side of this equation is a constant, all the terms in the equations have to be constants. Therefore, this term has to be constant, and y of t as t goes to infinity has to just be a number. Okay? Now, as t goes to infinity, if y of t is a number, then dy dt, the derivative of a constant with respect to time, is 0. d squared y dt squared is just the derivative of this. The derivative of 0 is just 0. This term goes away, and this term goes away. And as t goes to infinity, this equation simplifies down to omega n squared y of t is equal to a times u0 of t. Therefore, as t goes to infinity, y as t goes to infinity becomes a number. Y of t is a over omega n squared because u0 of t as t goes to infinity is just 1. This also gives us a chance to look at the circuit's DC gain. The DC gain, as you recall from our first order system response, is just the ratio of the amplitude of the output to the amplitude of the input as t goes to infinity. So the input amplitude is a, the output amplitude is a over omega n squared, so the DC gain of this system is 1 over omega n squared. Now, I determined all of this just by looking at the differential equation. This is extremely important. I can check this number relative to the circuit's response directly from the circuit in the same way that I did for first order systems. Okay? We can verify the DC gain from the circuit itself. Okay, as t goes to infinity, if you have a constant input, all the circuit parameters have to become constants. If the circuit parameters are constants, you can open circuit the capacitors and short circuit the inductors, you can look at the resulting resistive circuit, determine the steady state output response, and compare that with what you get from the differential equation. Okay, as we get to higher and higher order systems, okay, and we won't really go past second order systems much in this course, it'll become more and more important to check our results because there are more and more possibilities for making silly errors. So when you've derived the second order differential equation governing a circuit, it's extremely important to check the DC gain or the steady state circuit response relative to the physics of the circuit itself. Okay, make sure you do this step before you go on with any analysis associated with the differential equation you've written. The second order circuit parameter I want to talk about is rise time. As I mentioned in my introductory slide, graphically, the rise time is the time required for the response to get from 10% to 90% of the steady state response. Now, in general, when we look at these parameters, most of them will be normalized by the steady state response, which we talked about in the previous slide. Now, the rise time is intimately connected with the natural frequency, and in fact, the rise time for a second order system is approximately 1.8 over the natural frequency. So you can relate those directly via this approximate equation. Okay, the final second order circuit parameter that we're going to deal with is the maximum overshoot. Maximum overshoot is generally quantified by a number called m sub p. Now, as I mentioned earlier, all these parameters tend to be normalized by the steady state response. So the maximum overshoot is the peak response. Okay, you may want to go back to that graphical slide earlier and take a look at what that was, minus the steady state response. So the peak minus the steady state value normalized by the steady state value itself. This is often presented as a percentage of steady state. Now, the peak response, or the overshoot, is related directly to the damping ratio. And in fact, m sub p is e to the minus pi squiggle divided by 1 minus squiggle squared, as long as the system is underdamped. Recall that I said that these discussions are relative to underdamped systems. Okay? So you can use this if you want to find the damping ratio from a measured overshoot, or if you want to estimate the overshoot if you know the damping ratio of the system. This equation is a bit messy. On the next slide, I'll give an approximate relationship that's close to this for fairly small damping ratios. If your damping ratio is fairly small, you can often get by approximating the previous overshoot expression to this. M sub p is about 1 minus squiggle over 0.6. And that's not a bad relationship for squiggle less than 0.6. Okay? The smaller the squiggle, the closer this will be. And in general, approximations here are fine. Okay? Because we're just trying to get an idea of what the response is going to look like or estimate the governing differential equation from a measured response. We're not going to get things exact anyway. Okay, if we need an exact response, we'll have to go back and solve the second order differential equation exactly or numerically. Let's do an example of how we might use some of these concepts in order to determine something that we want to know. I have this circuit. Okay, I would like to determine the maximum value that the current I of t is going to see there. For example, maybe I'm burning out a resistor. Okay? Maybe I've designed this resistor relative to some steady state response of this circuit. Now I realize that that may not have been appropriate. I need to go out and do a transient or a time domain response to the step input in order to determine what currents are actually being seen here. Okay? So keep in mind, I want to find the maximum value seen by I of t. In order to do that, okay, if I don't want to solve the governing differential equation, I'm going to need the overshoot. Okay? The overshoot, m sub p, is based on a normalized steady state response, so I'm going to need the steady state response and the overshoot in order to find the maximum value I of t. Okay? So what we're going to do is write the governing differential equation. From the governing differential equation and the coefficients, we'll estimate the damping ratio and the natural frequency. The damping ratio and the natural frequency and the steady state gain will give us the steady state response and the overshoot. So our approach is going to be to write the differential equation, determine the coefficients of the differential equation, equate those coefficients to damping ratio and natural frequency. From that, I can find m sub p, the overshoot. That will give me, along with the steady state response, the maximum value of current. Now, as I said previously, when I write these governing differential equations, my approach is going to be to define a current through inductors and the voltages across capacitors as my unknowns. So my unknowns here are going to be I sub L of t, which is very conveniently I of t from KCL right there, and the voltage across the capacitor V sub c of t. So I'm going to take these two unknowns, write two equations in those unknowns, then eliminate V sub c of t in favor of I of t and get an overall second order differential equation in the current I of t. So I'm going to go to the next slide and do that process. Okay, here's my circuit again. I've labeled the unknowns that I'm interested in, the current through the inductor and the voltage across the capacitor. Now what I'm going to do is write two equations in these two unknowns and then combine those equations to get a single second order equation in I sub L of t, which is the same as the equation that governs I of t. So if I do KCL at this node, the current going into this node, which is 5 volts minus this voltage, which is V sub c, over this resistance, is equal to the current going out of this node, which is I sub L of t in this leg here, plus the current through the capacitor. The capacitor current is C dVc dt, which is 1 over 9 dVc by dt. So this is so there's one of my equations. One equation, two unknowns, Vc and I sub L. I need another equation. Let me do KVL around this loop. KVL will tell me that this voltage difference between here and here is the same as the voltage difference between here and here. Right? This resistor-inductor combination is in parallel with this capacitor. KVL tells me that this voltage plus this voltage, which is 3 ohms times I sub L, plus the voltage here is L dIL dt. L is 1, so this voltage is just dIL by dt, is equal to the voltage across the capacitor, which is just V sub c. Okay? There's a second equation also in the same two unknowns. I can combine these equations to eliminate V sub c. Let's take this equation here. I'll multiply through by 18 and take V sub c to the other side. So 5 is equal to V sub c plus 18 times I sub L plus 2 dVc by dt. Now I can eliminate Vc by substituting in from this expression. So Vc here is 3 I sub L plus dIL by dt. If this is Vc, then dVc by dt is just the derivative of this, which is 3 dIL by dt plus d squared IL by dt squared. So this term here becomes 3 dIL by dt plus d squared IL by dt squared. Combining all that leads me to my final result, which is 1/2 times 5 volts is equal to d squared IL by dt squared plus 7/2 dIL by dt plus 21/2 I sub L. There is my second order differential equation governing the step response. All I've done is substitute this in for this in for this, and done a little bit of algebra to get the leading term here equal to 1. So now we've got our differential equation in standard form. On the next slide, we'll look at this and identify the damping ratio and the natural frequency for this circuit. Now, from the previous differential equation, we can determine natural frequency, damping ratio, and the steady state value for the current through the resistor. Our governing equation turned out to be 5/2 is equal to d squared I dt squared plus 7/2 di dt plus 21/2 I of t, where I've taken advantage of the fact that I of t, the current through the resistor, is the same as I sub L of t, which is the current through the inductor. Now, this equation is in our standard form, so this coefficient here is omega n squared, and this coefficient here is 2 squiggle omega n. So to find squiggle, we need to know what omega n is, but we can determine omega n from this equality here. So omega n squared is 21 over 2, so therefore omega n is the square root of 21 over 2, which turns out to be 3.24 radians per second. Now we can employ the fact that 2 squiggle omega n is equal to 7/2. So squiggle is equal to 7 over 4 times 1 over 3.24, which turns out to be 0.54. Damping ratio doesn't have any units associated with it. The steady state response, I sub SS. This is the value of I of t as t goes to infinity. As t goes to infinity, everything becomes constant in this expression. So di dt goes to 0, d squared I dt squared goes to 0, and 21/2, 5/2 is equal to 21 over 2 I sub SS. So I sub SS is equal to 5 times 2 over 21 times 2. The 2's cancel. So I sub SS is equal to 5 over 21 amps. Now we've got everything we need to know. We need squiggle and I sub SS in order to determine the maximum overshoot, M sub P. Once we've found M sub P, we can find the maximum value seen by I of t. Okay, now we're finally set up to determine the maximum current. Previously, we found that the damping ratio was 0.54. 0.54 is a little bit too close to 0.6 for me to feel comfortable using my approximate relationship, so I'm going to go ahead and use the messy expression for M sub P. So I'm going to say M sub P is equal to e to the minus pi squiggle over the square root of 1 minus squiggle squared. If I use my calculator, plug that in, and run those numbers, M sub P turns out to be 0.133. Now, M sub P is defined as the peak value minus the steady state value over the steady state value. This peak value is what we want, but we need the steady state value in order to determine that. That's why we found that the steady state current was 5 over 21 amps. So to solving this expression for y sub p is equal to m sub p times yss plus the steady state response, multiplying through by yss and taking yss over to this side. So y sub p, which is just I max, is 0.133 times 5 over 21 plus 5 over 21 amps. That turns out to be 0.27 amps. We have gotten to where we wanted to get to, albeit through a fairly tortuous path. Okay, example 2 is intended just to give us a little bit more practice determining differential equations governing second-order circuits and determining initial conditions. So for this circuit here, I want to find the differential equation governing I of t and the initial conditions, current through the inductor at t equals 0 plus, and V sub c, the voltage across the capacitor at t equals 0 plus, where t equals 0 is when this switch closes. Okay? So I think we've done enough practice, enough examples to give you a pretty good chance of doing this problem on your own. So pause the video, give the problem a try, then you can come back and watch me do it. Okay, this is the appropriate circuit for time greater than 0. The switch has closed. This has become a short circuit between these two nodes. I'm going to write two equations in my two unknowns. My two unknowns being the current through the inductor, I sub L of t, and the voltage across the capacitor, V sub c of t. So I need to find two equations. I think the first one that I'll do is KCL at this upper node. So KCL tells me that the current into the node, which is 2 amps, is equal to the current coming out of the node, which is this current. Current through this leg is given just as I sub L. It's one of my unknowns. Plus this current. The current through the resistor is the voltage across the resistor, which is just V sub c divided by the resistance. Plus the current through this capacitor, which is just C dVc by dt. Pay attention to your passive sign convention. Current has to be entering the positive voltage node. Now I need one more equation. It's usually worthwhile standing back and looking at it for a minute. If I loop around here, I'll get a DIL dt term and a VC term, which is probably a good thing. So this voltage here is equal to this voltage here. So V sub c is equal to the voltage across the resistor, which is just the resistance times the current, plus this voltage across the inductor, which is just L DIL by dt. Again, current is entering the positive voltage node. Okay? Now, two equations, two unknowns, I can combine them to eliminate the unknown that I don't want, which is V sub c. If I plug this in there and dVc dt in here, that will give me an equation in I sub L. So V sub c is equal to this. dVc by dt is just the derivative of this. Okay, that is equal to R times DIL by dt plus L times d squared IL by dt squared. So making those substitutions, I have 2 amps is equal to I sub L plus 1 over R times R I sub L plus L DIL by dt plus, I want to plug this in here, so I have C times R DIL by dt plus L d squared IL by dt squared. Now I can group terms, solve for d squared IL by dt squared. So 2 is equal to, let's see, this cancels with this, so that's 2I sub L plus an L over R times DIL dt plus RC times DIL by dt plus an LC d squared IL by dt squared. That's an appropriate second-order differential equation, which is all I was really asked for. It's not in our standard form, but I don't need to determine the damping ratio and the natural frequency, so I'm going to consider myself to be done here. On the next slide, I'm going to go ahead and determine initial conditions on I sub L of t and V sub c of t. Okay, I want to determine initial conditions on the voltage across the capacitor and the current through the inductor just after this switch closes at t equals 0 plus. Now, the reason I'm picking those as what I want my initial conditions to be is because I know voltages across capacitors and currents through inductors cannot change suddenly. Therefore, I can solve this circuit for the switch open conditions and claim that these parameters are continuous with time. So first, let's look at V sub c of t. For t less than 0, this switch is open. The capacitor doesn't see any source terms. So this initial voltage, as long as this switch has been open for a long time, is going to be 0. So V sub c at t equals 0 minus is equal to 0 volts. We know that capacitor voltages cannot change suddenly, so V sub c at t equals 0 plus is also 0 volts. Looking at the current through the inductor. If this switch is open and has been open for a long time, this inductor is going to look like a short circuit. So I have 2 amps going through a resistance R and a short circuit condition here. This I sub L, if I do KCL here, just tells me that if this 2 amps is going here, the 2 amps has to go through this resistor-inductor combination. So I sub L at t equals 0 minus is equal to 2 amps. I know that inductor currents can't change suddenly, so I sub L at t equals 0 plus is equal to 2 amps. I've got the initial conditions that I want. Now, another nice thing about identifying currents through inductors and voltages across capacitors, as I keep mentioning, once you know the energy stored in the energy storage elements, you know everything else you need to know about this circuit. You can convert these, as we did in a previous example, to initial conditions on I sub L of t, which provide the initial current and the slope of the initial current. That will always be true. You can always find what you need as far as initial conditions from these initial values. For our next example, we're going to take the process we've been using previously and kind of reverse it. We're going to take a look at a given step response plot. From that plot, we're going to estimate the differential equation governing the system. So for this example, I have a system which I know is governed by a second-order differential equation. For example, maybe I've identified 2 energy storage elements in the system. I don't know anything about that system other than it is of the form a2 d squared y dt squared plus a1 dy dt plus a0y is equal to u of t, where u of t is the input to my system, y of t is the output for my system. Specifically, I don't know what the constants a2, a1, and a0 are. What I can do is provide an input to my system. My input happens to be a voltage. When I apply 10 volts as a step to the system, and I can measure the response, I get the following curve. Now, from our previous examples, we know how to relate the overshoot to the damping ratio. We know how to relate the rise time to the natural frequency. We know how to estimate the steady state response. In this particular example, what we're going to need to do is measure a rise time, an overshoot, and a steady state response, and essentially use those relationships in reverse to estimate damping ratio, natural frequency, DC gain. From that, we can determine A2, A1, and A0. Now, we've done a couple of examples that are very similar to this. At this point, you should stop the video, try to estimate these parameters, then you can come back, watch me do the problem. Okay, the first thing you want to do in solving this problem is to take a look at the plot and estimate the rise time, the overshoot, and the steady state response from the plot. Once you have those values, you can estimate the damping ratio, the natural frequency, and the DC gain. Once you have those, you can estimate the constants A2, A1, and A0. YSS is simply the final value that we go to in our step response. So Y sub SS is this value. It is 2 times 10 to the minus 3, which is 0.002. My overshoot is this distance here normalized by the steady state response. So m sub p is the peak value minus the steady state value, which is this height here, over YSS. This guy here is 0.005. 0.0005 over 0.002. 5 times 4 is 20, so MP is 1 over 4 times 100, which is 25%. Finally, the rise time is the time taken to get from 10% to 90% of the steady state response. 10% of the steady state response is about here. 90% of the steady state response is about here. So this horizontal distance is the rise time. This distance here is about 1 division, so the rise time T sub r is approximately 0.05 seconds. On the previous slide, we used the measured response data from a step input to determine that the overshoot was 0.25, the rise time was 0.05 seconds, and the steady state response was 0.002 for this system. Now we can use these to determine the damping ratio, the natural frequency, and the DC gain, which can be used to estimate the differential equation governing the system. From the overshoot, we know that m sub p is approximately 1 minus squiggle over 0.6. If we solve this, we can find that squiggle is approximately 0.45. From this equation, T sub r is approximately 1.8 over omega n. So omega n is 1.8 over T sub r, so omega n is 1.8 times 20, which is 36 radians per second. Now we have to use the DC gain of the system to determine the steady state response. If we write our equation in terms of a2 d squared y dt squared plus a1 dy by dt plus a0y is equal to u of t, that's equivalent to, if we divide through by a2, d squared y dt squared plus 2 squiggle omega n dy by dt plus omega n squared y is equal to 1 over a2 times u of t. This now will be 2 times 0.45 times 36. This term is 36 squared. We need to figure out what A2 is. We can use the DC gain to do that. So our equation is d squared y dt squared plus 2 squiggle omega n dy by dt plus omega n squared y is equal to 1 over a2u. If we take a look as t goes to infinity for this, it's a step response, everything becomes a constant. If everything's a constant, dy dt is 0, and d squared y dt squared is 0. Therefore, omega n squared YSS is equal to 1 over A2 times the final value of U, which is 10 volts. YSS is 0.002, omega n squared is 36 squared. I can solve this to get 1 over A2 is 0.259. Now we can use this result and this equation. So we said our equation is going to be of the form d squared y by dt squared plus 2 squiggle omega n dy by dt plus omega n squared y is equal to 1 over a2, which is 0.259 times u of t. Omega n squared is 36 squared. 2 squiggle omega n is 2 times 0.45 times 36. We know all the coefficients in the differential equation. We're done. This concludes lecture 23. We're now done with talking about analytical solutions to first and second order systems. Okay? The next topic that I want to do just briefly is what is called state variable models. I want to introduce us very, very briefly to time domain modeling of higher order systems. A very convenient way to do that is via state variable models. In general, that topic is not seen until the junior year. Okay, I want to at least introduce us to it now to prepare the way for seeing it in detail later on. So my next topic will be state variable models, and that will allow us to do some simulation of system responses using MATLAB. Most numerical analysis programs like MATLAB will deal directly with state variable models. They don't want to deal with an arbitrary nth order differential equation. Okay? PSpice, a common circuit analysis program, writes the equations for you in state variable form and then solves those equations. So these are kind of an underlying idea of a lot of things that go on numerically.